Welcome back. Today we're going to talk about the sampling distribution of p hat. And if you'll recall, p hat is the sample proportion. Okay, so what is a sample proportion? So let's say this for example. You get a bag of Reese's Pieces, and the manufacturer says that we guarantee that there is a 50% orange Reese's Pieces ratio. And this is important because obviously orange is the best Reese's Pieces. Piece of Reese's. Anyway, it's the best flavor, and so you want to make sure that you get your 50% because the other two, whatever their proportion is, you want to make sure you get 50% orange. Well, a sample proportion would be me saying, okay, I take this bag, I open it up, and I count the proportion inside this bag. Well, if there's 50 Reese's Pieces in this bag, I would expect that if the manufacturer is saying 50%, that there would be 50% in this bag of orange. Well, obviously, you can see how this could create a problem, right? Because a lot of things go into the dependence here, right? Is this an accurate representative sample? Do they have a true claim, right? Is there actually 50%? And what is the likelihood of me actually getting 50% orange in this bag when it's pulled from a gigantic sample? So maybe that 50% is not representative of my sample, but it is of the population. So we're going to look at different things like that today and figure out when can we use statistics to help us measure, is it unbiased, and what can we do, okay? So what we're looking at is sample proportion. So let's imagine that we're going to test this claim. We grabbed 1,000 bags of Reese's Pieces. So we don't have the population, but we have 1,000 different samples. And so what we're going to do is we're going to look at the mean and the standard deviation. Mean and standard deviation. Okay, so the mean of p hat, and this is a subscript, so it's down below. Excuse me. The mean of p hat should be equal to the true proportion. Okay, should be. Now we've got some conditions that need to be met, and we're going to talk about this in just a minute. But what should happen is if I do find the mean of the sampling distribution, mean of sampling distribution, right? If I do it right, if I have the right number of samples and have the right size samples, they should end up equaling one another out in the end. And my standard deviation of my p hat should be equal to square root of my actual proportion, my true proportion, times 1 minus my true proportion over n. So it's measuring the amount of successes or things that I'm looking to measure times, so true proportion is what I'm trying to measure. 1 minus p is the proportion of things I'm not trying to measure, right? So in this case, p would be the proportion of the orange ones. 1 minus p would be everything else. So the orange, or so the yellow and the brown. But the important condition on this is if the 10% condition is met. Right, and if you'll recall, the 10% condition is my sample less than 10% of the population, right? So if I have this this bag and I have 50 Reese's Pieces in there, well, obviously I'm less than 10% right there. So, but I've got to figure out, where am I at with my sample size? Okay, another thing that needs to happen is we need to test if it's normal. So I want to check for large counts, right? Is it large enough to call it normal? And my condition there is n times my proportion greater than or equal to 10, and is n times 1 minus p greater than or equal to 10, right? So if both yes, then it's normal. Why is this a problem? Well, you can't just go off and and calculate something using like a normal distribution, for example, if it's not normal. So you've got to test these two conditions before you can use like normal CDF on your calculator and do those kinds of things and use table A and that kind of thing. So you got to make sure you test those conditions before you start. The other thing that we need to consider is that in a probability, so probability of a sampling distribution so if p hat is, well, okay, if the sampling distribution is approximately normal, okay, so if it is normal, so if those conditions are met and you can use your table A, you can use normal CDF, then we can calculate our z-score. What a terrible z. Z-score by taking our p hat, subtract p, and then put it over our calculation for standard deviation, which is our proportion times 1 minus our proportion over n. Okay, so we can calculate a z-score that way. So then we can treat it as approximately normal and calculate things the same way. So calculate probabilities the same way. So let's look at a situation here. So suppose that 75% of young internet adult users from ages 18 to 29 watch online videos. I don't know if that's true. It's probably way higher than that. Just a guess of mine. A polling organization contacts a simple random sample of 1,000 young adult internet users and calculates the proportion p hat in the sample who watch online videos. Identify the mean of the sampling distribution of p hat. So think about this for a second. So what they've already stated is that 75% of young adult internet users watch online videos. Is that a statement about a sample, or is that a statement about the population? Think about that for a second. They didn't put any conditions on it. They didn't say in a group of 1,000. What they did was they said, hey, here is a statistic. And so this is a test of a statistic. So they'd say 75%. And I just said, I don't know if that's true. So what could I do? Well, I could test this. Well, what we're going to do is we're going to look at, like, what is it supposed to be? So identify the mean of the sampling distribution of p hat. Well, if this is true, and so 1,000 is my sample size, what I'm looking for is to say that the mean of my sampling distribution is actually equal to 0.75. And the thing is that this is gonna meet the 10% condition, right? Because 1,000 people 18 to 29, that's far less than 10%, right? And so what I can do is then I can, oh wait, hold on. This all should go up here. Mean of my sampling distribution is equal to 0.75. So down here, we want to calculate and interpret the standard deviation of the sampling distribution. So let's use our formula here. Standard deviation of our sampling distribution here is the square root of 0.75 times 0.25 over 1,000, which is our sample size, or n. And when we do this, we get 0.014. Well, what does that mean? So that 0.014 tells us the proportion of young adults that watch online videos in a sample of 1,000 typically varies by 0.014 from the true proportion of 0.75. So let me write that out for you. The proportion of young adults, this is our context here, right? Important. Young adults who watch online videos in a sample, important to say, right? So what we calculated was in a sample of 1,000. So it's important to provide the context, not only as young adults watching online videos, but also that it's in a sample size of 1,000. Typically varies from, varies by, I could have said it the other way, 0.014 from the true mean, sorry, we're talking about proportions here. Proportion of 0.75. So what does that mean? So we took our sample, we figured out what it was, and what we said was it typically varies by 0.014 from the true proportion of 0.75. So 75% of young adults supposedly do this, but it wouldn't be outside the realm of possibility to have something fluctuate a little from that, which is okay in a sample of 1,000, because obviously we know that every sample of 1,000 is going to have a different proportion, probably. And so it's going to typically vary by 0.014. So if I go 2 standard deviations on either side, we're looking at, 75. So let's see, 75 plus, 0.14. So 76, 77.8 down to, 73 or so. So somewhere in there is where we're going to find this population of young adults. So is the sampling distribution p hat approximately normal? So we want to check that large count conditions. So we're going to say is 0.75 times 1,000. Okay, so this is, remember up here, so is n times p greater than 10. So 0.75 times 1,000, yeah, that's greater than 10. That's 750. And 0.25 times 1,000, that's 250. So both of my conditions are met. So yes, actually I should say this. So we should say both greater than 10. I didn't mean to cross that out. That was an errant mark. There we go. So both of those are greater than 10, which means our large count conditions are met. So we can assume that this is normal, which, what does that do for us? Why do we even care? Well, now if it's normal, check out what I can do. I can find the area in that curve. So I can find probabilities. I can use my normal distribution setup. I can use my table A. So here's what we can do. So we say, yes, it is approximately normal. So if we find the probability that the random sample of 1,000 adults will give a result within 2 percentage points of the true value. So we're finding probability because it's approximately normal. What I can do is I can look at my normal curve here. Let me draw it out. And if we have 0.75 right here, which is our proportion that we're looking at, and we went within 2 percentage points, so we'll go 0.77 and 0.73. So what we want to do is, we can do this one of two ways, right? We can use table A or we can use Normalcdf. And so what we're doing is we're calculating with a mean of 0.75 and a standard deviation of 0.014. And we want to find the normal CDF between our minimum of 0.73 and our max of 0.77. Our mean is equal to 0.75 and our standard deviation is 0.014. So this, remember, that's necessary. I got to put that min, max, mean, and standard deviation. When we get that, we get 0.8472. So that means there's an 84% chance that it falls within this range of 73 to 77. Okay, so what we could also do is we could calculate it based on z-scores. So I'm going to put a big OR right here. And if we calculate our z-scores, we could do 0.73 minus 0.75. And we could go over 0.014 to get a z-score of negative 1.43. And okay, honestly, we could calculate it, but because it's 2 on the other side, we know that it's going to be equal to 1.43. But it'd be 0.77 minus 0.75 over 0.014. I should make that change up here, right there. Okay, so we use and that's the formula up here for z of a given population, or of a given proportion. So that's what we've got. So if we get a population of size where 9,000 instead of 1,000, how would this change the sampling distribution of p? So we made it 9 times bigger. The shape would still be the same. Right? Because we've already met those conditions to make it normal. So if we make it bigger, we're just making it more normal, maybe, I guess you'd say. It's still the same, so we'd say it's prox normal. Prox normal, okay? Center is the same, right? Center is the same. It is equal to 0.75. And so, and the variability is going to decrease, right? And I think that's the most important point of a question like this. The variability decreases. Why? Why would the variability decrease? Again, it's that sample size. So you put more measurements into this stack, and you get that thing that's kind of driven to the middle. So instead of being, more here and kind of like random scatter shot, you sort of get this filling in of all those values in the middle because you've got these sample sizes that are a little bit bigger. Okay, that's all I got on this one, guys. So thanks for watching, and we'll see you next time.